Lesson number 2 looks at determining how many possible solutions you could have in a system of linear equations. So this is the scenario that we have. 3 students are placed at 3 different burger restaurants. So at the Burger Shack, Deja charges $28 for 4 burgers and 2 salads, and $34 for 6 burgers and 1 salad. At the next restaurant, Shelley charges $18 for a burger and 3 salads, and $54 for 3 burgers and 9 salads. And at the Burger Haven, John charges $32 for 2 burgers and 4 salads, $42 for 3 burgers and 6 salads. So if we were to let X and Y, X is the cost of the burger and Y is the cost of the salad, at the Burger Shack, what would the equation $28 for 4 burgers and 2 salads look like? How would I write that as an equation? So X is the cost of the burger and Y is the cost of the salad. Equals 28. And what would the other equation be? Burgers and 1 salad is $34. So I'm going to give you a moment, and using that information for Big's Burgers and the Burger Haven, I would like you to write the equations from those 2 restaurants. So what are my 2 equations for Big's Burgers? X plus 3y equals, and?
3x plus 9y.
Okay, and in the Burger Haven, what would my 2 equations be? Okay, someone that I haven't heard from already.
3x plus 6y equals 42.
Okay, so we're going to look first of all at the Burger Shack. We're going to consider the equations for the Burger Shack because what I want to know is how much does 1 burger and 1 salad cost. So I want the solution to the system. So I have my 2 equations. 4x plus 2y equals 28. How do I put that into my calculator? What do you mean I can't? I have to isolate for y. So move the 4x over, which would make it negative. And then divide everything by 2. So if I divide everything by 2, I get y equals, okay? If I look at the other equation, 6x plus y equals 34, I want to start by isolating the y. And I get negative 6x plus 34. So if I go to put this into my calculator, so I clear my equations that I have. I've got negative 2x plus 14. And then I have negative 6x plus 34. Now, what do x and y represent again?
X is burgers and Y is salad.
The cost of the burgers and the salads. So if I go to my window settings, what I'm going to do is I am going to start at a -1, only so that I can actually see the x-axis properly. But what do I have to go up to? So think, what's a realistic price for the burger? The burger's not going to be any more than how much money?
Probably $5.
Probably $5. Even if I wanted to highball it, you go up to 10. It's not going to be more than 10 because 4 burgers at $10 should have cost me 40 bucks. So I definitely know that it has to be less than that. And the same thing for my salads. -1 to 10. So now I've got window settings settings that I can work with. Press graph. And there are my two equations. I'm not concerned about the x and the y intercepts at this point in time. Okay? What I'm concerned with is I'm concerned with this point right in here. So if I was to sketch that, I know that this negative 6x plus 34, if I made that my line of negative 6x plus 34, my negative 4x plus 28 has to start lower. Now, is the slope going to be steeper than this one or shallower? This one being 6, the other one being 4. Shallower. So then I find out my intersection point. Find that intersection point out for me and tell me what you get. So I get the coordinates of 5 and 4, and what does that mean?
Burgers are $5 and towels are $4.
There we go.
I was a little ahead of this, actually.
Okay, so let's do the same thing for our big burgers. I have x plus 3y equals 18. So I move the x over, which would make it negative, and then divide by 3. So I would get a negative 1/3 x plus 18. No, sorry, not plus 18, plus 6. And then with my 3x plus 9y equals 54, move my 3x over to make it negative, and then divide by 9. So negative 3 divided by 9 equals what?
Negative 1/3.
It equals negative 1/3 as well. And 54 divided by 9? What can you tell me about my two lines? They're the same line. They're collinear.
We only need to put one in.
So we only need to graph one line. Can I determine the cost of the burger and the salad? No, because their solutions, every point is the same, which means it could be this point, or it could be that point, or it could be that point. There's too many points to actually think of. So I can't actually determine the cost of the burger and the salad. So I can't determine one solution. Because there's more than one solution. Every point is a solution. Okay, so now let's look at Burger Haven. So I have 2x plus 4y equals 32, and 3x plus 6y equals 42 are my two equations. So if I isolate for y and move the x over, and then divide by 4. So what's negative 2 divided by 4?
1.5.
And 32 divided by 4? 8. Okay. The same thing with the other equation. Move the 3x over. And then divide by 6. So negative 3 divided by 6. Negative 1/2. And 42 divided by 6. 7. What do you notice about these two lines?
Pretty close.
Pretty close.
They're parallel?
Why are they parallel?
Because they have the same slope.
Their slopes are the same. So graph them. What does it look like?
You're not going to be able to find.
They're parallel.
They're parallel lines, what does that mean, Brianne?
They're never going to intersect.
They're never going to intersect, so is there a possible solution? No. So I'm going to get these two lines that are going to go like this and like this. So they're parallel lines, which means that there's no solution. So what does that mean in terms of what John charged for the burgers and the salads in the two orders? Did he do it right? No, he screwed up somewhere, because if he did it right, there should be a solution. There should be a common burger price and a common salad price between the two orders. There's no common solution. So how could I tell that John must have made an error in at least one of his calculations? The lines never intersect.
So, like, if you ever want to make sure that they're giving you a common price, sit there and recapping.
So when I have straight lines,
Good job.
if I draw two lines on a graph, how many times can I make them intersect? Is that the only possible way? So that would be intersecting once.
You do it twice.
How could I do it twice?
The graph goes like that.
Is it a linear equation though?
It's not, so you can't.
Okay. So I can make them intersect once. Can I make them never intersect? How? Parallel lines. Okay. Can I make them always intersect? If they're the same line. So this is none. And then if they're the same line, meaning I draw this line, and then I draw this line over top, we would say that there's an infinite number of solutions, because every little itty-bitty point, and I can zoom in and I can do another whole bunch of little itty-bitty points, are possible solutions. And to show you something on your calculator, because when you went to graph, if you had tried to graph this one right here, the negative 1/3 x plus 6, if you hadn't simplified this and you had just written it as negative 3/9, you might not have realized that the slopes, that these were the exact same graphs. If I had put that into my graphing calculator, I would have gotten negative 1 divided by 3x plus 6. And then if I did the next one and I went negative 3 divided by 9x plus, and I couldn't figure out 54 divided by 9, so I just typed it in like that. When I go to graph it, it draws this graph. And the little dots here keep traveling up and then they stop, which means it's done. But right now I have no way of actually knowing, did it draw both graphs? I can fix that. I can go down to my Y2 and I can go over to the end right here and I can press enter, and all of a sudden the line gets thicker. So now when I press graph, there's my first line, it's drawing it in. See how the line gets thicker? That's when it drew the second graph. So now I know that it's actually drawn both graphs and not that the second graph is just outside my window settings. Okay? So what I want you to do for your homework is I want you to do class example number 1 tonight. Class example number 1, and see if you can complete that chart for me. Okay, so the other day we looked at this problem with the Harper and the Smith family, and we graphed and we noticed that 3 types of linear equation graph systems can come up. We have the system where the graphs intersect at one point. We have the system where the graphs are actually the same, the 2 equations overlap each other. And then we have the system where the 2 lines were parallel. So I had you graph these equations in class example number 1 and then try to fill out the chart based on your observations. So if we look at this first one, I have x plus 5, which would go something like this. And then I have negative x plus 1, which would go something like that. And then I have this one intersecting point. And all you have to do is just say the number of solutions that were in the system. So this one has one solution. And that's how we can abbreviate solution. Then if I look at the next one, I have 2x minus 8, which would be a graph that would look like this. And then 2x plus 6, which would be a graph that looked like that. These are parallel lines. The graphs do not intersect. So in this case here, there would be no solution because there's no intersection point. And then the last one, in order to complete this one, I have to rearrange this equation. So we throw the 2y over to the other side because then it would be positive. Divide everything by 2, and I get 3x minus 2, which is the same as the first equation. So when I put this on my graphing calculator, that 3x minus 2 will give me this graph that'll go like this. And then if I change the thickness of the line, it would redraw another graph over top the first one. So in terms of the number of solutions, well, every single point along this graph is a solution. So we say that there is infinitely many. Because I can't count the number of solutions. If you tell me there are 15 solutions, I can find a 16. If you tell me that there's 115 solutions, I can find 116. So if we complete the following chart, what we have is we have the situation where there's one solution, no solution, and infinitely many solutions. Graphically, what this looks like is this, one solution means that the lines are intersecting at one point. So we just have to draw an example of lines that intersect at one point. That is an example of one solution. If there are no solutions, it means that the lines are parallel to each other. So I can draw parallel lines. And if there is infinitely many, then what I would have is I would have this same line drawn on top of itself. And if you want, you could use a different color to show that you're drawing the line on top of itself. So now if we look at the equations of the lines themselves. If I look at the slopes in particularly with the one solution, so that was this example in A, and it was also on the previous side. If we look at where we had one solution, that was these two equations right here. What you'll notice is that the slopes are different. So if I had just equations to look at, what I could say is that the slopes are different. And the intercepts, particularly the y-intercepts could be the same. They could be different. It doesn't really matter. What matters in this type of situation is that the slopes are different. If the slopes are different, I have one solution. Y-intercepts, that does not play a role in this. If I look at the equations of my parallel lines, and you guys pointed this out yesterday, they're parallel lines because their slopes are the same. The y-intercepts, though, have to be different. That's where you'll get them lying in different planes, as if they're intersecting that y-axis at a different point. So the slopes are equal, the intercepts are different. And then the final one that we have is if there's infinitely many. So when there's infinitely many, what ends up happening? Slopes are the same. The y-intercepts are also the same, because it is the same equation. So the slopes are equal. And the intercepts are equal as well. So now if we look at class example number 2, it asks, without the use of graphing, analyze the system to determine whether there would be one solution, no solution, or infinitely many solutions. So if I look at A, what I need to do is I need to make sure all of my equations are in a y equals form. So if they're not in a y equals, we need to write them as such. So if you want, you could pause this and you could go through the 3 equations and rewrite the 3 equations as a y equals. Okay, so now that you've done that, if I take this equation, I have to throw the 3x over, which would make it negative, and then divide by 5. So I get a negative 3/5 x plus 15. So what I have is I have the same slope. Intercepts are different, which means these are parallel lines. So there would be no solution. And the reason for that is they are equal slopes and different intercepts. So now if we take a look at B, I want to isolate in this equation, isolate y. So because y is negative, I'm going to throw it over to the other side. And then I'll divide by 4. So I get a 1/4 x plus 2 equals y, which is the same as the other equation, which now means I have infinitely many solutions. And the reason for that is because it is the same equation. And then if we take a look at the last one, I'm going to throw the 7x to the other side, which will make it negative. In this one, I'm going to throw the x to the other side. Or sorry, not the x, the y, which will make it positive. I'll bring the x over, or sorry, let me start over. Bring the 6y over, it will become positive. Throw the 5 over to the other side to make it negative. Divide by 6. Equals y. So we can see that our slopes are different. And because the slopes are different, there's one solution. And the reason for that is there are different slopes. So I would like you to practice with questions 1, 3, and 5. Or sorry, 1, 3, and 4, not 5. Okay, the last question in this section just looks at playing around with the window settings on a graphing calculator, which we did talk about a couple of times this year when we were looking at our graphing calculators. So at a local high school, the Students' Union decided to sell sweaters to students. The cost of designing the sweaters included a fixed cost and then a charge of $5 per sweater. Council plans to sell them for $25 each. The cost and revenue can be represented by the following system of equations, where D represents the dollar cost and N represents the number of sweaters sold. So in this case here, I do have to adjust my window settings. The way that I can figure out how to adjust my window settings, if I grab my calculator, is I start off by plotting in my y equals graphs. So I clear those two. We type in the 600 plus 5x, and then the 25x. And if I had decided to try to do this on a standard window setting, a zoom standard, nothing comes up, or something very small comes up, this line right here. So what I might want to do is I might want to take a look at my table. So I go second table. And if I look at my values, what I can see is that at 0 sweaters, it's already costing me $600. So I need to be a lot larger with my Y values. And then if I start scrolling down, what I'm looking for is I'm looking for when do these numbers start to match up? Or when does one start to overtake the other? So if I look at 22 sweaters, the cost is still more than my revenue. And now when I get down to 34 sweaters, I see that my revenue has surpassed my cost. But I'm at $800 at this point in time. So then if I look at trying to come up with a suitable window setting, which the graph kind of showed us, we knew that we were at 34 sweaters, so I could go up to 50, something nice and even. And then my tick marks, their scale that they have here to show us is up by 2s. So I could do that, or else I could just do 10s, because 10s are what is written. And then, if you remember, we were at $800. So again, I could round that up to $1,000, and I could go up by hundreds. And now when I press graph, there's my cost graph, and there's my revenue graph. And where the two graphs intersect is we're going to be the solution to that system. So take a moment and graph this on your grid paper that you have here. I have that 0. So when I go to graph this, because I actually have grid points and I have a scale on this grid, I should be a lot more accurate than I normally would if I was just doing a sketch. So I may want to use this table of values to help me out. Remember, if you go to second window, table set, you can set the table to be at 0 or whatever value you want, and you can also set it to be ask. And what that does is it allows me to input numbers. I could say, well, if I have 0 sweaters, what are my 2 points? 0 and 600. Well, now if I have 20 sweaters, I'm at 700. So that's my first equation. So my 700, that's the one that's in green. And then I'm at 500, that's the one that's in blue. Now that I have my 2 points, I can extend those straight lines. Now, if I were to find the solution to that, or sorry, we have a couple of questions first. How much profit or loss is made if 20 sweaters are sold? Well, I happen to already have input 20, and what I get is I get a cost of $700 and a revenue of $500. So if I put that in here, my cost was $700. My revenue, the amount of money I took in, was $500. So that's going to be a loss of $200. And now if I do the same thing for 50, and again I've got my table set where I put it on ask instead of auto. So if I type in 50, I get $850 for the cost and $1250 for the revenue. So cost is $850 and revenue is $1,250. So because I brought in more money, this time I have a profit, and it would be a profit of $400. Now, when you have these types of cost and revenue graphs, there's a break-even point. There's a point on the graph where there's no profit or no loss. That break-even point, that's the solution to the system. That's this point right here. This is my break-even point. And if I use my graphing calculator to help me solve that by using the intersection feature, second, calc, intersect, press enter 3 times, I get 30. I need to sell 30 sweaters in order to break even. So 30 sweaters allows me to break even. And if all 850 students in the school purchase a sweater, how much profit would you make? So what I can do is I can go into my table, because I don't have 850 on my graph. I only go up to 50. So I don't want to extend it that far, so I can use my graphing calculator in the table to help me find that. So 850 gives me $4,850 for the cost. So the cost, $4,850. Revenue, $21,250. So then the profit is the difference between these two values, which ends up being $16,400. That's how much profit I would make if everybody bought a sweater. And the other way that I could find these is I could plug 850 into the two equations. This one would be 25 times 850. That's how I would get the 21,250. And this one would be the 600 plus 5 times 850. Okay?
Staff better in the conference room.
So I would like to add questions 6, 8, 9, and 10 to this lesson.